So let's talk about what we can see but when we see the reduced or echelon form of these matrices. So for clarification, I didn't write down a matrix A and a matrix B. I just wrote down their reduced or echelon form. So this is A is some matrix, and this here is the RREF of A. And this matrix here is the RREF of B. So I didn't write down the matrices themselves. I wrote down where their pivots are. So when we talk about pivots, we want to talk about pivots in columns, and we want to talk about pivots in rows. If a matrix is an augmented matrix, then I will specifically state that this is the augmented matrix of a linear system. Or if we are given an equation or a linear system, then the matrix that we write down is most likely going to be an augmented matrix. We just want to make sure that when we're talking about a matrix, if we're talking about an augmented matrix, that has to be told to you. So if I didn't call it an augmented matrix, it's not an augmented matrix. So in this problem, we're just looking at some coefficient matrices, and we see where the pivots are. What we notice about the matrix A, we would say that the columns of A are linearly dependent because A does not have a pivot in every column. So we could conclude that the columns of A, are linearly dependent. Since A does not have a pivot in every column. The columns of A are linearly dependent since A does not have a pivot in every column. There are a couple other ways to write this sentence to express this idea, but this way will do it, so use this way. One of the things that we want to be careful is that you might say that A has no pivot in every column, which is not correct. You could say that column 3 does not have a pivot, but the reason that we're making the conclusion is we're saying that A does not have a pivot in every column. So we might as well just say that. Because when you say that column 3 does not have a pivot, it's less clear about why we're making the decision to declare the columns linearly dependent. What is it about column 3? Why are you specifically calling out column 3? The important thing is there's not a pivot in every column. So we don't need to call out a specific column. The important thing is there's not a pivot in every column. One thing to note is that when we're talking about linear dependence, that goes with the columns of A, because we were talking about a set of vectors. Dependence and independence goes with a set of vectors. So the columns of A are a set of vectors, but notice it's A does not have a pivot in every column. A matrix does not have a pivot in every column. A set of vectors can be linearly dependent. We do not want to say that A is linearly independent or linearly dependent. That doesn't make sense. A is a matrix. That's linear dependence is not about a matrix. It's about a set of vectors. We do not want to say this set of vectors has a pivot in every column. Pivots are a thing that belong to matrices, not sets of vectors. So this is important that we make these kinds of distinctions. For the most part, people will know what you're talking about, but you're being very imprecise in the way that you're expressing things. So we're declaring a set of vectors to be linearly dependent because a matrix does not have a pivot in every column. We can notice that the columns of A span R2. We can state that the columns of A span R2 since A has a pivot in every row. So we can conclude that the columns of A span R2 since A has a pivot in every row. Once again, span is something that goes with a set of vectors. A set of vectors does the spanning, but it's the matrix A that has the pivots. Set of vectors is what's doing the spanning, but it's the matrix that has the pivots. Set of vectors The set of vectors does the spanning, but it's the matrix that has the pivots. This is sufficient. This is all we need to say, and it has all the necessary conclusions, and everything makes sense. All the words go together. Those are the important things. We want to make sure that we write as much as we need, but as little as possible. Once we start writing more stuff, we take the chance of saying something that doesn't make sense. So that's why I want your explanations to be as efficient as possible. Any questions? So we can make similar observations about the matrix B. We say that the columns of B are linearly independent since B has a pivot in every column. Done. Say no more. We would say that the columns of B do not span R3 since B does not have a pivot in every row. And then that's sufficient. That's where we need to stop. Any questions? All right. So I just made this distinction between a matrix and a set of vectors. We often think of the columns of a matrix as a set of vectors. So if we're going to use some set of vectors words like linear independence or span, then we need to be talking about a set of vectors like the columns of a matrix or a set of vectors. So if a set of vectors, let's say S equals V1, V2, V3. So this set of vectors could be linearly independent or linearly dependent. This set of vectors does not have any pivots because it's not a matrix. So this is a set of vectors. So there's a set of vectors. Now we want to analyze this set of, if we want to analyze this set of vectors, we may construct a matrix out of it. So the matrix that we would construct to work with this set of vectors would be this matrix, V1, V2, and V3. Now I'm defining a matrix by its columns. Notice that curly brackets with commas, we're listing the vectors in a set. If I write it in square brackets, I'm making a matrix, and I have no commas, I'm just listing the vectors. So set of vectors, curly brackets with commas. So a set of vectors will have curly brackets and commas. A matrix will have square brackets and no commas. So we might say something like this set of vectors is linearly dependent because the matrix does not have a pivot in every column. So we might take this matrix, we do some work on this matrix and find this is row equivalent to 1, 0, 2, 0, 0, 1. So we see a pivot in the first and the third columns. So if this is the RREF of the matrix, we could say something like this set of vectors v1, v2, v3 is linearly dependent this set of vectors is linearly dependent since the matrix v1, v2, v3 has a pivot, does not have a pivot in every column. So the set of vectors is linearly dependent because the matrix does not have a pivot in every column. It's the matrix that has the pivots. It's the set of vectors that's linearly independent. All right. So there is a pending question about talking about an equation being consistent. So A and B can both be coefficient matrices in matrix equations. So let's take a look at that example. So I'm going to reproduce the matrix. I actually just have to write the matrix B because it doesn't have name. It just has a name. So here's the matrix B, and it's row equivalent to 1, 0, 0 by columns, and then 0, 1, 0. So B is some 3 by 2 matrix that is row equivalent to 1, 0, 0, and then 0, 1, 0, where we see there's a pivot in the first column and a pivot in the second column. So we can conclude that the columns of B are linearly independent since B has a pivot in every column. So we would say that the columns of B are linearly independent since B has a pivot in each column. So the columns of B are linearly independent since B has a pivot in each column. So notice that I'm looking at the reduced to echelon form of B, and that's telling me where the pivots are. The pivots do not change because we've done row operations. If doing row operations would change the pivots, then the pivots wouldn't be useful to us. So we don't have to say since the reduced to echelon form of B has a pivot in each column, we just have to say B has a pivot in each column. So for example, this one's actually easy to create. If B looked like this, 1, 2, 3, and then 2, 5, 6. This is row equivalent to 1, 0, 0, 0, 1, 0 by columns. And there's a pivot in the first row, first column, second row, second column. There's a pivot in the first row, first column, and the second row, second column. We don't have to say that that the pivots are in the reduced to echelon form. It's important that we don't say that the reduced to echelon form of B has a pivot in each column, because that is hiding the fact that it's B that has the pivots. And it's opening yourself up to the interpretation that you think the pivots depend on which row equivalent form we're dealing with. So you want to say that B has a pivot in each column. The reduced to echelon form is just what we use to find out where the pivots are. So it's not the reduced to echelon form has a pivot in each column. B has a pivot in each column. Any questions? The equation doesn't matter. Notice that I've said nothing about an equation in this case. This is completely independent of if we're putting this in a matrix equation or anything. So it has nothing to do with any kind of equations. So let's write the other conclusion that we see. We can see that B does not have a pivot in each row. So we would say that the columns of B do not span the columns of B do not span R3 since B does not have a pivot in each row. So the columns of B do not span R3 since B does not have a pivot in each row. Any questions? So when we're looking at linear independence, one way to define linear independence is to say that Bx equals 0 has the equation, the columns of B are linearly independent if Bx equals 0 has only the trivial solution. Those are all important things. We can't leave out any one word of that sentence. The columns of B are linearly independent if and only if Bx equals 0 has only the trivial solution. The way we determine if Bx equals 0 has only the trivial solution is by finding out that B has a pivot in each column. So this is why this is explanation through pivots. Explanation through pivots. If we can use a matrix and the pivots of the matrix, that's the best thing to do. So these are statements where we use linear independence and spanning R3, talking about a set of vectors. These are both statements that we made about a set of vectors. So these are set of vectors things. We can talk about an equation, a matrix equation. So we could say, since the columns of B do not span R3, because B does not have a pivot in each row, that means we could say that Bx equals, I'll use a different vector, Bx equals P is not consistent for all P in R3. So this statement here about the span is equivalent. This statement about the spanning R3 is equivalent to saying that Bx equals P is not consistent for all P in R3. So this statement is exactly equivalent to saying that Bx, I'm going to use Q because everything has to rhyme. Bx equals Q is not consistent for all Q in R3. Bx equals Q is not consistent for all Q in R3, and we decide that by saying since B does not, spell does correctly though, that would help. Since B does not have a pivot in each row. There, I went on to make more sense. Bx equals Q is not consistent for all Q in R3 since B does not have a pivot in each row. So once again, here we're making a conclusion about about an equation. So now this is an equation, specifically a matrix equation, but we'll say an equation. And we're saying consistent. Consistent is a word that goes with an equation. We would not want to say the equation is linearly independent. That doesn't make any sense. But the equation is consistent because the coefficient matrix B does not have a pivot in each row. Any questions? As far as linear independence goes, so we see that the columns of B are linearly independent. That means that if Bx equals Q is consistent, then the solution is unique. That's what we get out of the linear independence. But Bx equals Q is not consistent for all Q in R3, but that means it is consistent for some Q in R3. If Bx equals Q is consistent, then the solution is unique. So this linear independence statement, we could say that if bx equals q is consistent, then the solution is unique. And this is because the columns of B are linearly independent. The columns of B are linearly independent, and we say that because B has a pivot in each column. So once again, we're making a statement about an equation. And we're saying consistent, and we're saying unique, and that's what goes along with consistent and solutions are unique. Oops, solution is unique. Shouldn't have split the line on that one, but consistent with unique solutions because B has a pivot in each column. All right. So there's no formula for saying for all Q or for some Q. You just have to say what you want to say. I could rephrase not consistent for all Q in R3 by saying inconsistent for some Q in R3. But if you're looking for a formula of when to say for all and for some, don't. You just have to learn what the things mean so that you say the right things. We are past the land where we can just formulate our responses. Any questions? Going back to equation talk, here's the matrix A. We could say that AX equals Q is consistent for all Q in R2 because A has a pivot in every row. The solutions to AX equals Q are not unique because the columns of A are not linearly independent. And that's because A does not have a pivot in every column. Any questions? We can also make statements about the matrix multiplication and the linear transformations that are associated. But I want to talk in more detail about linear transformations before we do that. Any questions on our phraseology? All right, let's pause the video and then talk about linear transformations.